Hello everyone, welcome to today's webinar. Today we're going to go over Unit 2. Unit 2 is about polygons and triangles. Within this webinar, we're going to go over the most challenging topics that you may find in this unit. Before we start, that's myself. My name is Miriam. I joined the team here at Penn in 2015. I am certified to teach high school math since 2010 in the state of Pennsylvania. And also I did earn my master's last year. Today in this webinar, we're going to go over various kind of topics that you will find in your lessons or unit. We're going to go over interior angles in polygons. We're going to go over some special polygons like parallelograms and quadrilaterals and see the different properties for these shapes. And also we're going to go over the triangles, areas for triangles, Pythagorean theorem. We will go over congruency and similarity as far as triangles, polygons, and segments. If you have any questions during this webinar, you are able to type in your questions in the questions box. And please keep your questions relevant to what we speak about in this webinar. Also, all registrants for this webinar will receive a recording after a few hours after the conclusion of this session. To begin with, we want to understand more about the shapes. So any closed shapes with straight sides, we call polygon. So we have triangles, they are essentially polygons. Quadrilaterals, any polygon with 4 sides, this is what we call quadrilateral. Pentagon, 5-sided polygon, hexagon, and so on. From the name of the polygon, you'll be able to decide the number of sides in each figure, and also the number of the sides will equal to the number of the interior angles in those polygons. Now, the popular ones that we deal with a lot with geometry are triangles, a different kind of triangles like right triangle, isosceles triangle, for example. Quadrilaterals, we know that rectangles and squares are essentially quadrilaterals. Trapezoids too is one of them. Parallelogram. In this webinar, I'm going to go over parallelograms a little bit and go over the properties that a parallelogram has. So a parallelogram is a quadrilateral because it has 4 straight sides. And the parallelogram is different than a trapezoid, for example, because each pair of sides that are opposite, they are equal in length and parallel. So if I wanna label my figure, so I would signify that this side and this side are parallel. I'm gonna do that by using the arrows. So this side here and the opposite one are parallel and equal in length. And the other pair of the opposite sides are parallel as well, and they are equal in length. So that will tell us the properties as far as side length and parallelism for the sides on the parallelogram. Now we have this angle and this angle. These opposite angles are congruent. Congruent means they have the same measure. They have the same measure. So if this is 100 degrees, for example, so that one, the opposite one should be 100 degrees. And we're talking about the parallelogram. So these are the special properties of parallelograms. The same way, if I'm having this as 100, so that would be 80, and that would be 80 degrees. These two opposite angles are congruent. Another property that we are able to find in parallelograms is that 2 consecutive angles, they are supplementary. From webinar 1, unit 1, we did learn that any 2 angles, if they add up to 180 degrees, we are able to call them supplementary pair. So any two consecutive angles in any parallelogram should add up to 180 degrees. And in this case, we call them supplementary. So this angle plus this angle is 180 degrees. This one plus the one consecutive to it is 180 degrees. Within your lessons, there are many properties to the different polygons and parallelograms and trapezoids. So go over the lessons and try to make yourself a shape like this and label your squares or rectangles or trapezoids with the properties of each one so you're able to be familiar with it. In the exam, I have seen some questions about the properties of some of those polygons. So make sure that you go over them, maybe make yourself a note, or again, make yourself a figure like that. If you just joined us in this webinar, you're able to ask your questions using the question box to type in your question. The raise your hand feature is not enabled in our webinars. Okay, well, polygons. Well, any polygon, as we said, is an n-sided closed shape. An oval, for example, or a circle is not a polygon because the perimeter of the circle is not consisted of straight sides. Although it's a closed figure, but circles are not polygons. So a polygon, something like this that you see in the screen right now, it is a closed shape. It has straight sides. Now, if you are asked to find the sum of all interior angle measures in a given polygon, what should we do? Now, there is a formula, and if you look over geometry, really, we're not going to invent the wheel. What we have to do is to get familiar with a formula that was proven in the past by scientists or mathematicians. And then our job is to know how to use the formula correctly and when to use them. So don't think that you need to think deeply about if the formula is correct or no. All you have to do really is to use them correctly and decide which formula to use. So to find the sum of all interior angles inside any given polygon, you are able to use the formula here. The sum equals to 180, just a number in the formula, so we're going to use it as is, times n minus 2. What's n? N is the number of the sides in the polygon, or it's the same as the number of all interior angles. So if you count all the sides or you count all the interior angles, then that would be the value of n that you will be using to find the sum of all interior angles in a given polygon. So this is a given polygon. Let's count the sides. What I like to do, I'm going to label my first side that I'm going to count so I don't count it twice. So that's 1, 2, 3, 4, 5, 6, 7, 8. So I have n equals to 8. That is actually an octagon. It's not the familiar one that we have in mind, but because it's an 8-sided polygon, we call it an octagon. So how can we find the sum of all interior angles in an octagon? Use the formula. S to the sum equals to 180 times 8, because that's the n, minus 2. A common mistake is that students would multiply 180 times 8 and then subtract 2. That is incorrect. With the order of operations, we need to consider the parentheses first and then we multiply. So we're going to evaluate this expression by doing the subtraction first inside the parentheses. 8 minus 2 is 6. And then we multiply the 6 times 180, and that will give you 1,080 degrees as the sum of all interior angles in an octagon. Any questions? Anything that was not clear or did not make sense on that screen? Okay, let's move forward. You will see that throughout the webinar, we're going to have some self-check questions. These questions will be practice for you, not graded. I'm not going to keep track of who did do them correctly or incorrectly. That is merely offered in this webinar for your own practice. So let's look at the next question about polygons, but this time we are talking about a special kind of polygons, regular polygons. So regular polygons are polygons that have all the sides in that polygon have the same length, like a square, for example. A square has 4 sides, and each side is equal to all the other sides. So in that case, we are able to call a square a regular polygon. The one that we have on the screen, we can determine what kind of a polygon or n by just counting the sides. So I'm going to label my first side so I don't count it twice. 1, 2, 3, 4, 5, 6, 7. 7, so n equals to 7. So that tells me that this is a heptagon. And let's read the question. If the polygon shown is a regular polygon, find the measure of angle C. So we're looking for the actual measure, not the sum, the measure of one of the interior angles. In the regular polygons, since all the sides of the polygons are equal in length, it is true that all of the interior angles have the same measure. So, in my mind, I'm thinking if I'm able to find the sum of all interior angles in that regular heptagon, I can just find the sum, divide over 7, and that will give me the measure of one angle inside that one regular heptagon. And this is what the question is asking. So here's the plan. Let's do the sum, the same formula that we have used in the last question, 180, parentheses, n minus 2. It is a good habit that you write the formula before you use the formula. Sometimes when we recall the formula from our mind, we may drop the parentheses. We may write the minus as a plus. So it is good to write down the formula before we use it. So n is 7. The sum then would be 180 times 7 minus 2. Again, order of operations. We're not going to do the multiplication yet. 7 minus 2 is 5. 5 times 180 will give you 900 degrees. This is not what we're looking for in the question. The measure of one interior angle, let's call it C. So the measure of angle C equals to the sum divided by n, which is 7. And that will give you 128.6 degrees. So each one of these angles in that regular heptagon will measure 128.6 degrees. Questions? Okay, let's look at a self-check question. Again, with polygons. So each interior angle in a regular decagon measures what? How many degrees? How many degrees would each interior angle in a regular decagon would measure? In this question, we have two keywords, regular and decagon. How many sides a decagon will have? And how can we use the fact that the decagon is irregular? In a little bit, I'm going to leave you do the calculations. I'm going to remind you of the formula because you have it in front of you. S equals to 180 times n minus 2. You need to find n, use the formula correctly, and choose the correct answer. In about a minute or so, I'm going to change my screen to the same question, but this time you'll be able to submit your answer. So take your time, use the formula, and choose the question. Choose the answer. The question is there. Okay, I'm going to switch my screen so it will give you again the same question, but you'll be able to submit your answers. And here you go. So what is the interior angle for each of these interior angles in a regular decagon would measure? I always remind my students after we do the self-check, we do the question together. If you find that you did not do the question correctly, it does not mean that you will fail, or it does not mean that geometry is not your subject, or it doesn't mean that you will never get geometry. It just means that you need to go back to the lesson, read over the particular part that talks about the sum of interior angles or regular decagons or regular polygons, and then do the webinar again. Watch the webinar again and do the questions again. So let's do the question together. So to be able to find the interior angle measure for one angle inside a regular decagon, first I need to find the sum of the angles and then divide over n. And since it's a decagon, I know that n equals to 10, even though there is no figure provided. But from the name of the polygon, I was able to determine n. So s equals to 180 times 10 minus 2 equals to 180 times 10 minus 2 is 8. So 8 now times 180 will give you 1,440 degrees. That's the sum. I do not need the sum. I need the measure of one interior angle. So measure of angle, let's call it C, equals to the sum divided by 10, because n is 10, equals to 144 degrees, and the answer is going to be D. Any question? Anything that was not clear? Anything that does not go along with the readings that you have done, if you have done any for that unit? Okay, let's go to the next topic, exterior angles. So again, we're talking about polygons. So what if we are asked to find the measure of an exterior angle this time, not an interior angle? To find the measure of a specific exterior angle within a polygon, first find the measure of its adjacent interior angle. Then find the measure of the exterior angle using the supplementary relationship of the pair. What does that mean? If we look at the figure here, the question is asking us to find the measure of angle GAAP. GAAP. So this one is asked of us to find the measure of. This is an exterior angle. Now, if you look to the angle adjacent to it, it's an interior angle inside that polygon. And also you will notice that FAG is a straight line. That tells us that the angle FAG is a straight angle. A straight angle measures 180 degrees. So that means that the angle, the exterior one, GAB and BAF, are both supplementary pair. So if I'm able to find the angle measure of the interior angle and then use the supplementary property for these two angles, then I'll be able to find the measure of the exterior one. In this question, you are asked to apply too many information, too many knowledge. So in an exam question, for example, do not expect it to be straightforward. I mean, if it's straightforward, that is great. But if it's not, then you need to think about using multiple things that you've learned in unit 1 or 2, for example, and combine them to arrive to the answer. So our plan is to find the sum of all interior angles in that polygon. Now, since all of the angle measures inside that polygon except this one are given, we can figure the angle measure here by subtraction. And if we know the angle measure here, then subtract that from 180 degrees because these are supplementary pair, and that will give us the measure of the exterior angle. Let's do that. So I'm going to use sum equals to the same formula, 180 times n minus 2. What's n? Let's count. That's the first 1, 2, 3, 4, 5, 6. So n equals to 6. That is a hexagon. So since I know 180 times 6 minus 2, that will be the same as saying 180 times 4, because 6 minus 2 is 4, multiply, and that will give you 720 degrees. This is the sum. I do not need the sum. Just an intermediate step for me to get to my answer. Now, if I am able to do subtraction, I'll be able to find the measure of this angle. So measure of angle, that's the interior one now, BAG equals to the sum, 720, everything inside the interior minus the known angles. So minus the sum of all of the other angles that we know the measure of. So 90, remember that square or box here represents the right angle. So that is 90 degrees plus we have 100, we have 120, we also have another 100, and finally we have 150. The way we're going to do that, we're going to evaluate the expressions, the sum inside the parentheses first, and then do the subtraction. So 720, you can use a calculator or you can do that by hand for adding these values. If you add them up, you will find the sum is 560 degrees equals to, now subtract. That's everything minus or except that one missing angle. So that will give us the measure of the interior angle missing. And that will be 160 degrees. Now we know that this is 160 degrees. We can use the supplementary property because this is a straight line. So these are supplementary pair. So the measure now of angle, the exterior one, BAG equals to, or GAB, it's the same angle, would be the 180, the supplementary property, minus the adjacent one, 160, and that will give you that the exterior angle measures 20 degrees. So that is 20 degrees. Any questions? Okay, coming up is a self-check on the same concept, exterior angles. This time we have a polygon, but it's a triangle. So what is the measure of the angle ACD? So what we're trying to look for is the exterior angle measure. Now, we know that we can use the formula 180 times n minus 2 and so on to find the sum first, but we know for a fact that the sum of all interior angles in any triangle measure what? It measures what? How many degrees? It's a fact. Okay, I'm going to leave you with this question. Think about the sum. Do the same as we did and decide if finding this angle will help you to find the exterior angle. I'm just leaving the screen up so you're able to see the figure, because the second screen with the same question does not have the figure. So I'm going to leave that for another few seconds until you put everything down on paper, and then I'll change my screen where you can submit your answers. Okay, let's look at the question on the other screen, and you can submit your answers. Again, those questions are not graded. I do not keep track of who did that correct or incorrect. This is provided just for you to practice, to see which area in this unit that you want to definitely review before taking the exam. I'm going to wait for another 10 seconds for everyone to have a chance to participate in this question. Okay, let's do the question together. We know for a fact the sum of all interior angles in any triangle is 180. If you'd like to use the formula, you will find out the same result, that the interior angles, they add up to 180 in any triangle. So the sum is 180. So if I'm able to find the measure of angle AC B by subtracting the 180 minus the sum of the other two known angles, so that is 50 plus 66, so that will give me 180 minus the sum, which is 116 degrees, so that is 64 degrees, and this is for the interior angle, but this is not our question. The question is asking this angle measure. So these two angles are adjacent and they make up a straight angle, so they are supplementary pairs. So 180 again minus the interior one will give us the exterior angle measure, and that will give us again 116 degrees, and the answer is B for this question. Other questions? If you have questions on those topics, it's a good time to answer those questions for you before you get back to your studies on this unit. Okay, let's move on to triangles. The area of triangles. Within your study unit, there are two possible formulas that you're able to use to find an area of a given triangle. The one, you need to use the base of the triangle and the height of the triangle. Multiply them together, take the half, and that will give you the area of the triangle. Or there is more complicated formula where you're not given the height of a triangle, but you're given the length for all three sides of the triangle. So you determine which formula you need to use based on the givens in each triangle. So in the green triangle on the left, you are given the side length 3, 2, and 4 units. So that would make us not to choose the first formula because I don't have the height. I do not have the height. None of those sides are the height of the triangle. So I am forced to go ahead and use the one with the square root. So this formula looks overwhelming or complicated, but we're going to do it step by step. If you do your math correctly and you use the formula correctly, you will end up with the correct answer. So the formula for the green triangle would be the area equals to the square root of S times S minus A times S minus B times S minus C, and notice the parentheses. That would mean that we have to do the evaluation of this expression under the square root sign a certain way. Now, what's A, B, C, and S? S is the half of the perimeter of the triangle. S equals to half of the perimeter. The perimeter is add all the sides together and take the half, and that will give us the value of S in this triangle. So 3 and 2 and 4 divided by 2 will give you 4.5. So the value of S that we're going to use in this formula 4 times is 4.5. What's A, B, and C? They are just the sides, the side length. So I'm going to call 4 to be the A, side A. I'm going to do this one to be B. You can then do this to be C. You can change those labeling, but the answer will be the same. So area equals to, now we have all the values of S, A, B, and C. S is 4.5, 4.5 times. We're going to follow the formula times S again, 4.5 minus A. A is 4. Then times S again, 4.5 minus B. B is 3. And then 4.5 minus C, and C is 2. Okay? Still looks overwhelming, but we need to simplify the expression. We are not going to multiply yet. We will do the subtraction inside each parenthesis first. So 4.5, the first one stays as is. Do the subtraction. 4.5 minus 4 is what? Is 0.5. That's a 0, 0.5. And then 4.5 minus 3 will give you 1.5. And then 4.5 minus 2 will give you 2.5. Note that we're still multiplying. So those parentheses with no operation signs means that we have to multiply these 4 values together, equals 2. Multiply using your calculator. You can do it manually. I would prefer with decimals to use the calculator, so because we're not learning how to multiply really. We are learning how to use this formula to find the area of a triangle. So just to avoid any distractions, I like to use a calculator in this case. So multiply 4.4 times 0.5 times 1.5 times 2.5 equals 2. And your answer under the square root sign still would be 8.4375. Now we're going to evaluate the square root expression. So on your calculator, however it works, you may have to do the sign for the square root and then the value under it. Or maybe some other calculators you have to enter the value under the square root and then punch in the sign. So however your calculator works, you need to know which order you have to punch it in your calculator. The square root of this value is 2.9. Since this is an area for this triangle, so our units would be squared units. So if this is like 4 centimeters, then the area would be squared centimeters, for example. So this is the area of the triangle. We did use this formula again because we were not given the height of the triangle. Any questions on this part of the slide? Anyone is not clear how we did end up with this number? Okay, let's move on to the second case, another triangle. This time we have a different set of givens. One of them is an altitude or height. DC is the height of the triangle. How did I know that DC is the height of the triangle from the figure? It's not in the words of the question, but in the figure, it is a segment connecting a vertex to the opposite side, and this segment is perpendicular to this side. So that's why I did determine that DC is the height, and AB, because this is the side where it's perpendicular to this segment, that would be the base of the triangle. So this is the base. this is the base, and this is the height or the altitude. The formula that is consistent with our givens is the first formula, because the base, which is AB, is given as 7 centimeters. DC is given as 4 centimeters. There is an extra information given in this triangle, which is BC, 5 centimeters, and we do not need that. Sometimes in exam questions, you're given too many givens. So you need to determine which ones that you need and which ones that you just have to ignore. Okay, so area equals to half times the base times the height equals to half times the base again is the side where the altitude is perpendicular to. So BA is the base, which is 7 centimeters. The height is 4. You can use a calculator or you can do mental math. Half of 4 is 2. 2 times 7 would give you 14, and the units would be centimeters squared. This is the area of the blue triangle given here. Any question? Okay, let's move on to the next question, which is a self-check question. Examine the triangle ABC, then answer the following question. It's only one question. The altitude in this triangle is what? Which side or which segment is the altitude of this triangle? Now, the special thing about this triangle, before I leave you think about that answer, is the triangle ABC is a right triangle. Some sides are perpendicular to each others. What is the altitude or the height in this case? What do you think? Is it AC? Is it BD, this segment that connects that vertex to this side? DC? Or BC? What do you think? Where is the height in this triangle? And this kind of question will help you if the question asks further to find the area, you will know where is the altitude and where is the base. I'm going to leave you with this for a few seconds and then switch to my other screen. Okay, again, the question without the figure this time. Which one is the altitude or the height on this triangle? And here you go. Remember that the height or the altitude should be perpendicular to one of the sides of the triangle. If it's not, then that's not the height given. So think about perpendicular sides or perpendicular segments to another side and try to find which one that we are able to call a height for this triangle. Few more seconds and then we go over the question together. Marcy, you are correct. I did do a typo in my answers, so I'm gonna then do the question together because the answers on my screen are the ones that has one correct from the given 4. So which one in your mind would be called an altitude or a height? okay? And that is BC. So BC is the height of the triangle. In this case, the triangle is a right triangle. So the side BC, not a segment this time, because again, it's a right triangle. And let's go over the definition of an altitude. It connects a vertex with the side, and also this segment or side is perpendicular to the other or the opposite side. So in this case, BC is the height, and that would make AB the base. Next question. On the same triangle but more givens, the area of the triangle ABC is what? Try to draw yourself that figure on paper and determine the formula that you're going to use. I'm going to write down both, and you determine which one. It's either the area equals to half times the base times the height, or you can use area equals to the square root of S times S minus A, S minus B, and S minus C. Which formula do you think would be possible for us to use? And if it's possible, then do you have a second choice? Can you go with the easier, or you have to stick with the harder one because that's the only one that you can use in this question? And again, ABC is a right triangle. What do you think? What is the area in square centimeters for this triangle? Okay, before I go to the other screen, you're given the length sides of all three sides. But are you provided also the altitude and the base, or no? Do you have an option to choose from these two formulas, or you have to go with the harder one? Okay, I'm going to change my screen and do the question later together. What is the area of that triangle that we had on the screen? A few more seconds, and then we can go over this question together. Okay, let's do the question together. So again, we have a triangle. We are provided some givens. In this triangle, it's a special kind of triangle because it's a right triangle. With right triangles, the altitude is the same as one of the sides, and the other side that has the right angle in the corner will be the base. So I am able to use the harder formula if you'd like, because I have all the givens necessary for that, but I'm going to go with the easier one. Both of them will give you the same answer. So it's up to you which one you feel comfortable using. I'm going to use the easier and shorter one. So area equals to half times the base times the height equals to half times the base. Let's determine the height. So the height can be BC, and then the base can be the BA, or I can think about it differently. If AB is the altitude, which is it can be, because it's again connecting a vertex to the other side and it is perpendicular, then BC would be the base. Since it's a multiplication in this formula, it's not going to matter the order. So let's take the base as the 10 AB, and the height would be then the BC, which is 5. You can do that using a calculator or mentally. 10 times half. So half of 10 is what? 5. 5 times 5 is 25. 25 centimeters squared. This side length AC was given to you to confuse you, to make you choose AC as one of the heights or the base for this triangle. So you should not use this side length because it does not belong to this formula. Any questions? Okay, let's move on to right triangles. Whenever you hear the word right triangle, you always think about the Pythagorean theorem. This is so special to only right triangles, and it's only true if the triangle has one right angle. Pythagorean theorem says that in any right triangle, the square of the hypotenuse is the side facing the right angle. So this is the right angle. The side opposite to that would be the hypotenuse. So it's again, the square of the hypotenuse equals to the sum of the squares of the other two sides in that right triangle. So this is theorem again special to right triangles. I have seen students using this theorem with any other triangles, which is not going to be giving you the right answer. So what's the area of the triangle ABC? Again, from the figure, maybe it's not in the wording of the question, but this box at the corner of the triangle gives you the information that this is a right triangle. What's the area of ABC? Let's see what's given first. I have one side and the other side. So the formula that needs to use the height and the base, we cannot use that because we have the height but not the base. The other formula with the big square root sign calls for the three side lengths, and we have one missing, so we cannot use this formula either. What can we do? Using the Pythagorean theorem here, we are able to solve for the missing side length. And from there, we can either decide to use the square root formula or the shorter one, half times the base times the height. So let's do that together. So the Pythagorean theorem says c squared should equal to a squared plus b squared. So the c and the a and the b, they are not the angles. The angles are given in capital letters. The little c, little a, and little b we usually use for sides. Okay, so the given is here. One of them is the length of the hypotenuse, which is c. So 10 squared, since this is a right triangle, should equal to a squared unknown plus b squared. So b squared is given 5 squared. Don't forget to square the values because the formula asks you to square it. 10 squared is not 20. So 10 squared is 10 times 10, 100, equals to a squared plus 5 squared again is not 10, it's 5 times itself. So 5 times 5 is 25. Now it's a simple equation in one variable. Remember, when we are solving equations in one variable, we need to isolate the variable. So a should be by itself in one side and everything else on the other side. I see the a squared, our variable, is added to 25, then do the opposite, subtract 25 from both sides of the equation to keep it balanced. 25 minus 25, that's gone. 100 minus 25 is 75, equals to a squared. I do not need a squared now, I need a, the length of CB. So to do that, do the opposite of squaring the a, take the square root on both sides. So that will give you a equals to the value of the square root of 75. Use your calculator and you'll be able to find the a equals to 8.66 inches. So now we have the a. Since the question is asking us for the area, we have the altitude and the base, or the altitude and the base, then we can go with the easier formula. Area equals to half times base times height equals to half times, let's say that CA is the base, for example, so that would be 5. That will make CB the height, which is the value that we just found, 8.66, multiply everything together, and that will give you the area of this right triangle is 21.65 squared inches, since we're talking about area. So again, in this question, it's a complex question. You had to use Pythagorean theorem. You had to use equation solving methods. You had to use the area formula to find the answer. So get prepared in the exam that you may have to use multiple steps to find your answer. Any questions on this problem? Okay, let's do a self-check question on the concept of Pythagorean theorem. Examine the triangle XYZ, then find the length of side YZ. So YZ is the one missing here. It's not asking us for the area, but it just asks us to use the givens in the figure to find the length for Z, Y, or YZ. What is so special with this triangle that we are able to use to find the missing side length? I'm going to leave that screen for a while, like about a few seconds. Draw yourself the figure, put the givens on the figure, and think about the special property about this triangle. Okay, so at this point, you must have been thinking about the triangle being right triangle. I want to remind you of the formula. C squared equals to A squared plus B squared. Where is the C? Where is the hypotenuse? Which one is that? This side or this side? Okay, let's move on to the other screen. And again, what is the side length for YZ? A few more seconds and we can do the question together. Okay, let's do the question together. Again, since the triangle is a right triangle, I feel confident to use the Pythagorean theorem. So again, the hypotenuse squared equals to the sum of the squares of the other legs or arms of the triangle. So my major task in this formula is to determine which one of the sides is the hypotenuse. Again, the one facing or opposite to the right angle. So xy 10 centimeters is the length for the hypotenuse. So I'm going to use the formula. 10 squared equals to, or should equal to, a squared plus b squared. Let's call this a and this b. You can switch. So a squared, that is 7 squared plus the unknown variable squared. 10 squared again is 100, equals to 7 squared is 7 times 7 is 49, plus b squared. We have one unknown. Do the opposite to isolate the variable, minus 49 and minus 49 on the other side as well. That's gone. 10 minus 49 is 51, equals to b squared. We're not looking for b squared, we're looking for the side length for b. So take the square root and take the square root on the other side, and that will give you value of b. The square root of 51 is 7.14 centimeters. So the answer is A. Any question? Okay, I'm gonna go a little bit over time. If you want to stay, you're welcome, of course. If you cannot, then you will receive the recording of this webinar in a few hours after we conclude the session. Area of quadrilaterals. There is no specific formula given to us in our units or lessons that will make us use the formula and calculate the area of a given quadrilateral. There is like a roundabout way that we are able to use our knowledge until now to find out the area of a given quadrilateral, like this one, SVUT. If you notice, this quadrilateral is divided into two different triangles, triangle number 1 and triangle number 2. Well, we know how to find the area of a triangle. So if I'm able to find the area of triangle 1, find the area of triangle 2, add them together, that will give us the area of this quadrilateral. So we know the two formulas that we have options to use for the area of a triangle, either half times the base times the height, or the other one with a square root. Now, none of the triangles that we have has an altitude given, so we have to use the harder formula for each triangle to find the area of each triangle. I'm not going to go over the details on how to do that. We went over that formula already. I'm just going to give you the S in each case, and then you're able to use the formula and then add the areas. But I'm going to give you also the final answer. So S in the first triangle, add up the perimeter and divide over 2. So that will give you 7 plus 5 plus 4, then divide over 2. So in this case, S is 8. And then you're going to use the formula S times S minus A times S minus B times S minus C, and so on. You can determine which one is A, B, C in this first triangle. Do the operations like we did in the previous slide. You will end up where you have the square root of 96. Take the square root of 96, and that will give you 9.8 squared inches as the area of the first triangle. Second triangle, the same method, just different numbers. Add the perimeter to find S, and then divide over 2. Divide over 2. And that will give you 5. So your S now is a 5. Again, use the same formula. You're going to do the steps until you find that the square root of 20 will give you the 4.5 squared inches as the area number 2, which is triangle number 2. This is not our final answers. We still have to add the areas. So A equals to A1 plus A2. Add the two values, and that will give you the area of the quadrilateral. So 14.5 should be your final answer for the area. Questions on this slide? Okay, let's move on to a major topic in this unit, which is triangle congruency. Congruency, again, is when two shapes are the same. They have the same everything, the same side lengths, the same corresponding angle measures. They are just copy-paste. So there are three methods that we are able to use, or three tests that we're able to use to determine if two given triangles are congruent. So the three ones I have are these three. These are what we call them. This is the shorthand of the method or the property. And I just gave you an example, just a little example, just to remind you about the property. The first way that would make two triangles congruent is that if we find that each corresponding side pair have the exact length. So the purple sides, these are corresponding sides in the two triangles. If this is 5 and 5, 3 and 3, 4 and 4, then I can conclude that these two triangles are congruent. And we call it SSS, side, side, side. The second way, if it's true, that would make the two triangles congruent would be if I have two angles, two pairs of corresponding angles. So this purple here in this triangle and the corresponding one on the other triangle have the same measure. Another pair, the green ones, this angle and this corresponding angle on the other triangle have the same measure. And the connecting or included side, the red one, have the same length, then I am able to conclude that these two triangles are congruent. ASA, angle, side, angle. The last property that if it's true in two triangles, then they will be congruent is if I have the sides, two pairs of sides. So the red one and the red one on the other triangle have the same length. Another side, the green ones, are corresponding and have the same length. And the included angle also have the same measure. If that happens, then these two triangles are the same copy. They are congruent. And this property we call side angle side, SAS. Let's look at an example just to apply the knowledge that we had about triangle congruency. Before we go, I need to mention this important note. If two triangles have the exact measures of each corresponding angle in both of them, that would not make them congruent. So I want to give you an example because this is a common mistake. If I have a triangle and another triangle, I have this angle with this angle have the same measure. This one here and this one have the same measure. And if this one here with the corresponding one have the same measure, we cannot say that this triangle and this triangle are congruent. We cannot. They may be congruent, but it's not a definite result of congruency of corresponding angles. So be careful. If that happens, that the three pairs of corresponding angles have the same measure, we call them similar triangles, not congruent. So that is a trick question. Make sure that you understand the difference between congruency and similarity. Okay, a question on congruency for triangles. The two triangles QRS and ABC are congruent. So it's given as a fact, a given in the question that these two triangles are congruent. So now we need to decide by which property that makes us say or confirm the given in the question that these two triangles are congruent. Side, angle, angle, side, side, angle, or angle, angle, side. Which one that makes us say, yes, they are congruent? In these two triangles, you have side and the side corresponding to it have the same length. QS and the corresponding AC have the same length. What about the included angle? Are we able to confirm that the included angles also have the same measure? What do you think? Use the givens. I'm going to keep that on the screen. Try to put that on paper. Think about the question and choose the property that makes us say that this triangle is congruent. These triangles are congruent. Okay, let's do the question together. Or I should give you the question first to submit your answers, and then we do the question together. So a few seconds, since the figure is not available on that second screen. Which property you think is the right property to say that these two triangles are congruent? Okay, let's do the question together. Okay, so again, we have two pairs of corresponding sides, this side and that side, the same length, this side and the corresponding one, the same length. The angle, though, the angle is what's missing. So since the first triangle ABC has two other angles known, and we know that the sum of the interior angles in any triangle is 180, we can subtract the sum from 180. So that would be 30 plus 67. And then do 180 minus the sum, and that will give you the missing angles measure, 83. So that is 83. So we have also, beside the two sides, the two pairs of sides being congruent, also the included angle have the same measure. So the property for that is side angle side, SAS. That is the right property. Any questions? Okay, let's go over similarity. So two similar triangles, how do we determine if two triangles are similar? Now it comes the time for the AAA, angle, angle, angle. So if we have three pairs of angles, the corresponding angles have the same measure. So angle B have the same measure as E, angle A have the same measure as D, and angle C has the same measure as angle F. Then we are able to say that these two triangles are similar. We cannot say that they are congruent, but they are similar. So this case, AAA is the property. Another condition, if it became true, or we were able to prove that it's true, that will make the two triangles similar, is that when there is a proportion between the corresponding sides of the triangle. So example, if this is 10 and this is 5, if this is, for example, 6, let's say 6 and 3. If this is 20 and 10, then they are similar. Why again? Because there is a proportion. This triangle is double the size of this triangle. How did I know the proportion? 10 over 5 is 2. 20 over 10 is 2. 6 over 3 is 2. So there is a fixed proportion between the side length of corresponding sides for all three in each triangle. And that is written by giving the relationship AB divided by DE. So AB divided by the corresponding DE equals to AC divided by the DF, the corresponding one in the other triangle, and then BC divided by EF. All of these fractions, if they are equal, then the two triangles are similar. Example. The triangles QRS and ABC are similar. So again, it's given as a fact that they are similar. Then in our mind, whenever we hear the word similar in triangles, polygons, or segments, we know it's about proportions. It's about two or more equal fractions. What's the length of side QR? What's the length of side QR? I'm going to set up the proportion with you. I'm going to leave you to solve the proportion. So again, similarity, meaning right away two equal fractions. We need to set up the fractions correctly though, or we're going to get the incorrect answer. So we have RQ, that's the unknown. That's the unknown. RQ is here, this one. The corresponding side in the other triangle is BA. So I need to put that right under it on the same fraction. Since other pair of two sides, they're corresponding, and also we know the measure or the length of that, then we are able to use that as a reference. So on the top, we had RQ coming from this triangle, then the top value on the other fraction should come from the same triangle. So RS divided by BC should equal to RQ divided by BA, because it is known that the triangles are similar. Fill in the information. Do you have RS? Do you have BC? Do you have RQ? No. Do you have BA? Set up the proportion and solve the proportion. And that should give you directly the side length for RQ. I'm going to leave that for a few minutes, few seconds again, and switch my screen. Here you go. What is the side length for RQ? Knowing that the two triangles are similar, we did set up the proportion correctly. Then what is the side length RQ? Okay, let's do the problem together. So fill in the blanks. We have 5 over 15 equals to RQ, which is the unknown, over BA. So BA is actually known. So that would be the BA, which is 20. My way of solving that proportion is multiply and then divide. So RQ equals to multiply, cross multiply 5 times 20 divided by 15, and that would give you the 6.67 inches as the side length for RQ. And again, that was possible because the two triangles are similar. Similar polygons, the same concept. Proportion. So whenever we hear the word similar, we need to think about proportion. With polygons, it's a little bit different proportion because we have squares. So if two polygons are similar, then we need to use this proportion instead. The area 1 over area 2 of the other polygon equals to the square of one of the sides on the first polygon divided by the square of the corresponding side in the second polygon. the question that we see on the screen. Let's read that together, and that will demonstrate the use of that proportion. One side of a polygon whose area is 24 square meters. So let's say that this is area 1, that is 24, and has the side 7 meters. What is the length of the corresponding side if the similar polygon has area of 72, and that is area 2? What should we use? The proportion. So area 1 is given 24. Area 2 is given 72. The other fraction, we have to square the values. So side 1 from the smaller polygon is given, but square the 7. And then the unknown would be the square of the side number 2 from the second polygon. Again, that would give you 24 over 72. Square the 7, 49 over the square of the other corresponding side. Solve the proportion, cross multiply, and then divide. So that would be 49 times 72 divided by 24. Use your calculator. You're going to figure out that the square of the other side is 147. We still have to take the square root of 147 because we have the value of the square. So do the opposite. The square root of that value would be 12.12 meters. So again, similar polygons, proportion. Do the proportion correctly. Don't forget to take the square roots afterwards to find the missing side length. Same type of question, two similar polygons. Use the proportion. Again, I'm going to remind you of that before I leave you to do the question. A1, area 1 divided by area 2 would equal to the square of side 1 over the corresponding square length of the other polygon. Let's call this area 1, area 2. Let's call that x1, and that would be the x2. What should we do? What is the side length AB in the similar polygon? You have A1 is 50, A2 is 15, square the 10, and that would be your missing variable. What would be the side length? Okay, here's the question again. That is the last question, I promise, in this webinar. You had the 50 over 15 equals to 10 squared over the unknown squared. What would be the side length, not the square of the side length, the side length of the other polygon, given that they are similar? Okay, let's do that together. So again, I'm going to fill in the blanks. Area 1 is 50. Area 2 is 15. They are similar, then the fractions are equal. Equals to 10 squared. Since this is coming from the bigger polygon, then this value will come from the bigger polygon again. And then that would be x2 squared And that would mean that 50 over 15 equals to 100 over x2 squared. x2 squared equals to 100 times 15 divided by 50. Multiply and divide. That will give you that the square of the side is 30. Then take the square root to 30 because we want the side, not the square, and that will give you 5.48 inches, and that would be answer A. That's it. So again, similarity means proportions, two equal fractions. The last topic in similarity, the same thing. Segments are similar when there are some kind of proportion. The segments become similar if you have multiple parallel lines cut by two transversals. So HK and LO are transversals. That would make those segments here proportional or similar. This question will explain how can we go about that. Find the length of segment MN. So MN, this one is missing. If the length of the segments HK 10, LO is given as 8, and then IJ is 4, what would be the segment length of this? Given that this is a system of parallel lines cut through by transversal, that would make the segments similar. Again, the word similar means equal fractions. So I'm going to set up my fraction like this. HI from the first transversal over J over HK. So I have, so that transversal given two segments, we're going to use the IJ, the given IJ, over the same transversal segment here, HK, that should equal to MN, and then the longer one that corresponds to this one is LO. So IJ over HK should equal to MN over LO. Fill in the blanks again. IJ is 4 divided by 10 for HK equals to MN is the missing value. LO is given as 8. Solve the proportion, cross multiply, and then divide. MN equals to 4 times 8, and then divide over 10. And that will give you that the segment MN is 3.2 centimeters. Any questions? Okay, that concludes my math part of the webinar. We did go through multiple topics today. Interior angle measures in polygons, exterior angle measures in polygons, triangles, right triangles, quadrilaterals, Pythagorean theorem that corresponds to the right triangles, congruency and similarity between triangles, polygons, and segments. Now, how to study for the exam? Of course, you need to read the unit. You want to do the practice questions. The answer key are provided for those questions for a purpose. So you need to learn from those answer keys and then either reach out for help or maybe redo the question until you get the right answer. You can watch that webinar again whenever you receive the recording. You are able to reach out for help by calling the school from 9 to 6 on weekends. You are able to schedule an appointment with an instructor or teacher assistant and come with actual specific questions on the lesson, or you can text message learn, and one of us will get back to you. You are able to email or chat through your portal. You have either this kind of portal or this kind of portal. Both have the same functionality, just we change things around. So follow the instructions that correspond to your account. You will be able to email or chat with one of us here about your questions. And that is it for the webinar. Thank you for your participation and your attendance as well. There is a small survey, very short, 3 questions that will tell me how I did do throughout this webinar, or if there is any improvements you would suggest to see on the future webinars. Before I leave you, if you have any questions, I'll be happy to answer them. Okay, good luck in the exam. I hope I did cover the topics that you had in mind for this unit. Have a good day.